Hello, myself Dr. Sundar Chaudhary. Good morning to all students. Today I will teach you application of NMR spectroscopy. NMR means nuclear magnetic resonance. So that application is an important part of NMR spectroscopy. So that the primary application of NMR in the field of structure determination and delineation. There is a literature of NMR spectra comparable to those for optical absorption spectra and X-ray diffraction spectra. Comparison of the NMR spectrum of an unknown compound with these in the literature may lead directly to identification of the unknown compound or complex. Today, NMR has become a sophisticated and powerful analytical technology that has found a variety of applications in many disciplines of scientific research, medicines, and various industries. Modern NMR spectroscopy has been emphasizing the application in biomolecular systems and play an important role in structural biology. In addition of NMR provides unique and important molecular, motional and interaction profiles containing vital information on protein functions, and the information is also critical in drug development. Here, some of the application of NMR spectroscopy are listed below. The first one is uh, qual- uh, the first one application of NMR is qualitative analysis. In qualitative analysis, a large number of principles are known which will decide about the structure of an unknown forms its NMR spectrum. Some of these are outlined as follow. You can see in the slide. The number of main NMR signals should be equal to the number of equivalent protons in the unknown compound. And second one important point is the chemical shift indicate in any molecule of spectra of NMR of the any molecule, that what type of hydrogen atoms are present. For example, like methylene, methyl groups, olefins, ethers, etc. And third important point, the spin splitting or multiplicities reveals about the possible arrangement of groups in the molecule. And last one is the from the area of peaks in the spectra, one can draw the conclusion about the number of hydrogen nuclei present in each group. For example, the relative areas of methyl and methylene peaks in CH3, CH2, CH3 would be 6:2. In the case of butane, it would be 6:4. So that NMR is particularly useful in the identification of organic compounds. The chemical shifts indicate what types of hydrogens are present. For example, methylene, methyl groups, olefins, aromatic compounds, and esters. The spin splitting indicates it's spin splitting, or you can say also it multiplicity indicates what groups are next to each other in the molecules. Another piece of information is obtained from the relative size or area of the absorption peak in the spectrum, which tells us directly how many nuclei, means how many hydrogen atoms are in each groups. For example, propane, the ratio of the areas of methyl and methylene peaks would be 6:2. The next application of NMR is quantitative analysis. Mean to that, here we explain of this. Here I will take example of case of this type of application, means qualitative analysis. NMR spectroscopy has been used to determine the molar ratio of the components in a mixture. If the NMR spectrum of mixture of compound is recorded, it may exhibit a resolved band due to one of the components. And if the number of protons in the molecules giving rise to that band is known, then the integrated area of the band will give a direct measure of the relative concentration of that component in the mixture. So in the case of you can see in the slide, here I am taking example of three component system by NMR. So in the case, peak heights rather than the areas can be correlated with composition, because in these cases the signals chosen are extremely narrow and their width depends upon the uniformity of the magnetic field. This can be illustrated by recording an NMR spectrum of a three component system having equal quantities of benzaldehyde, ethyl alcohol and toluene. You can see in the figure, A is aldehyde, it's mean benzaldehyde, C6H5CHO, and B is in the figure is ethyl alcohol, C2H5OH, and C is denoted for toluene, C6H5CH3. So from the figure, the heights of the peaks of aldehyde, hydroxyl and aromatic methyl groups are marked by ABC respectively. The relative heights of the peaks A, B and C are recorded, and the relative heights, the composition we can calculate by the spectra, by the peaks values. So that from the above figure, the heights of the peak of aldehyde, hydroxyl and aromatic methyl groups are marked by ABC respectively. The relative heights peaks ABC recorded and composition can be calculated, so that you can see in this table the major relative heights of compound A, B and C is 1, and for ethyl alcohol it would be 1.9, and for toluene it would be 3.4, and relative these values are measured relative heights, and the calculated relative heights for A, B and C compounds for it 1, 2.02 and 3.33. The composition from NMR data, it would be 33.3, 32.3, 34.4. You can see in the table. The NMR spectroscopy is very useful in analysis of a mixture of isomeric substitutory compound like ortho and metaparazine. This is also another application of quantitative analysis of NMR. And third one application of NMR is hydrogen bonding. The NMR can be used to study the hydrogen bonding in metal chelates as well as in organic compounds. Proton signals is shifted toward low field in the case of hydrogen bonding. That reveals that hydrogen bond information results in the decrease in the electron shielding of the proton. If there occurs an upfield shift of the signal, this may be ascribed to the breaking of intermolecular bonds. This can be seen in the case of ethanol on increasing temperature or on diluting the ethanol with the carbon tetrachloride. So that the shift associated with hydrogen bonding arise from three terms. The first one is the electrostatic effect of the donor atom or group, and second one is the diamagnetic anisotropy of the donor atom or group, and depend on the third point, changes in long range shielding of the acceptor group. In the case of strong hydrogen bonds, the factor I is dominant. However, the factor second, in the case of strong hydrogen bonds, the factor first is dominant. However, the factor second may be become dominant in the case of weak hydrogen bonds. And the factor third possesses little experimental foundation. It is only operating in the case of intramolecular hydrogen bonding, and this factor third is important in explaining the gas solution shifts for acetylene and hydrogen bonds. Some workers have attempted to correlate the proton shift of chloroform in several solvents, but the solvents with the strength of the corresponding hydrogen bonds. But no quantitative relationship between magnitudes of low field shifts and hydrogen bond strengths could be established. So, this study has provided quantitative identification of bond strength. And fourth important application of NMR is structural determination. Structure, you can see in the slide. Here I am taking some structural analysis, structural examples of structural examples of explanation of this type, this important application of NMR. First one is structure of SOF4. In the case of SOF4, when the 19F spectrum is recorded, it shows only one signal in the low field. This reveals that all the 4 fluorine atoms in the SOF4 molecules are equivalent. Therefore, the NMR spectrum support the following structure of SOF4. In the case of ClF3, when the 19F spectrum of ClF3 is recorded, it shows 2 types of fluorine signals. This reveals that there are 2 types of fluorine atoms in ClF3. The NMR spectroscopy supports the following structure. And the another important application linkage isomerism. In the case of linkage isomerisms, so you can see in the figure, here I am taking example unusual chelate compound, that if a ligand can, in the case of compound first in linkage isomerisms, if a ligand can be bonded to a metal in several alternative ways, the NMR spectroscopy can be used in some cases to show which particular linkage isomer is present. An interesting example you can see in the slide. It is unusual chelate. According to the Figgis and co-workers, the structure of this complex first, but after acidify of above complex, get a yellow complex recorded by NMR shows 3 methyl signals at 8.37, at 8.94, and 8.08 in a ratio of 1:1:2, and a peak at negative 2.47 tau due to hydrogen bond proton. When this data provided by NMR are interpreted along with IR information, so one may assign the formula of second. It is obtained a yellow complex. So another one is how to determine ligand isomerism by NMR spectroscopy. In the case of acetyl acetone, you can see in the figure, here I am taking one example for explaining ligand isomerism for formyl cobalt acetyl acetone. So in this case, NMR spectroscopy has been used to study this ligand isomerization and this proportionation. This proportionation of some unsymmetrically substituted metal acetyl acetone when formyl cobalt acetyl acetone is heated in boiling toluene at 111 degrees centigrade for 48 hours. The chelate undergoes ligand isomerization to yield a mixture of 6 components in the resulting mixture, which has been confirmed by TLC. We can confirm by TLC, and identification of the various compound in the mixture is done by comparison of their NMR spectra with those of the other authentic examples of, we can take also cobalt chelates, one of the components identified by the ligand isomer shown in the figure you can see in the slide. So the NMR data is also follows that ligand isomerism is an intramolecular process, and the disproportionation of the cobalt chelates involve a lower energy of activation than that of similar chromium chelates. If you compare with chromium chelates of so another one is structure of, we can another one structural determination point is structure of polyethylene. You can see in the slide. The NMR spectroscopy is very useful in the study of polyethylene, which has wide application of tremendous scope in our daily life as well as in industries. If the NMR of polyethylene is recorded, it shows two types of lines. One of these is narrow while the other is broad. Both are superimposed on each other. The narrow component is ascribed to the amorphous phase, whereas the broad component to the crystalline phase. This result is in agreement with the result obtained by X-ray analysis. You can compare NMR spectra with NMR spectra of this polyethylene compound with the X-ray analysis. And the another important application of NMR is keto-enol tautomerism. We can explain by NMR spectroscopy. In this case, here I'm explaining the acetyl acetone. The NMR spectroscopy is here I'm taking one example, acetyl acetone, for explanation of keto-enol tautomerism. The NMR spectroscopy is very successful in studying keto-enol tautomerism. In the case of acetyl lactone, the following equilibrium exists. You can see in the figure CH3, CO, CH2, CO, CH3. It is a keto form, and CH3 and CH3 bonded with COH. This part of keto form and this part of enol form. In this reaction, the NMR spectrum of acetyl lactone is recorded. You can see this spectra you can see in the figure in the slide. The peaks are assigned to OH, double bond CH and single bond CH3 groups of the enol form, and to the CH2 and CH3 groups of the keto. It means keto. The assignments of band is based upon the fact that the ratio of the integrated areas for the methyl and methylene protons in the keto form should be 3:1, and that the methyl and methine protons methine protons in the enol form it should be 6:1. From the NMR spectrum, the areas of CH2 and CH peaks are carefully measured, and it has been found that the acetyl acetone at 25 degrees centigrade contains 18.6 plus minus 0.6 keto forms. This value is more accurate as compared with the value of 24% obtained by bromine method. The another important application of NMR is intramolecular conversion. Here we are taking one example for explanation of this type of application. Here I am taking PF5 example. When the in the intramolecular conversion from the electron diffraction study of PF5, it is clear that the compound, it is a gonal dipyrimide and contains two non-equivalent kinds of fluorine atoms. This clearly shows that the NMR spectrum of PF5 should be different NMR signal. When the NMR spectrum 19F of PF5 is recorded, it shows a 1:1 doublet whose separation does not depend upon field strength. This reveals that 5 fluorines are equivalent and their signal is split to a doublet by coupling with the 31p nucleus, 31p nucleus, and its spin state would be half. This rather anomalous result has been explained by suggesting that in PF5 there occurs intramolecular rearrangements which are rapid enough to prevent the appearance of separate signals for atoms lying structurally non-equivalent sites in a molecule. Berry called this type of behavior as pseudo-rotation and gave a schematic representation. You can see in the slide. The pseudo-rotation is a vibrational process and it is not involving any bond breaking process. So thus the could explain the equivalence of 5 fluorine as well as the spin coupling between the 31p and 19f in PF5 molecules. And next one, important application of NMR spectroscopy of determination of activation energy. Here I am taking N and that's dimethyl acetamide. It's mean it is also called DMA compound for estimation of determination of activation energy. The application can be illustrated by taking a well studies example of this DMA, because you can see in the structure of DMA, because of the large separation there is no spin coupling between protons on different methyl groups. When the NMR spectrum of DMA is recorded at 30 degrees centigrade, the spectrum shows a single peak. You can see in the spectra of DMA in the slide, single peak and a doublet indicate that two methyl groups attached to the nitrogen are not equivalent. Magnetic equivalence of these methyl groups can be released by increasing the rate of rotation, that is by heating the compound. Thus, as the temperature of DMA is increased, the peak of the doublet begin to broaden and ultimately convert into a single line at about 90 degrees centigrade. Their rate of rotation may be given by, you can explain, you can say K is equal to half tau. Here K is the rate of rotation and tau is the mean lifetime of the particular configuration, which is related to the line width and line separation of the methyl peaks. The value of tau can be measured at any temperature using the appropriate equation. So the activation energy delta E may be calculated by using the Arrhenius equation. And the another important application of NMR is elemental analysis. In elemental analysis, NMR spectroscopy can be used for the determination of the total concentration of a given kind of magnetic nucleus in a sample. Forbes and Jung Nickel have investigated the integrated NMR intensities of the protons peaks for a large number of organic compounds and have calculated the accurate quantitative determination of total hydrogen in organic mixture is possible. And the another important application of NMR, rates of reaction. An interesting special use of PMR spectroscopy, its mean proton magnetic resonance spectroscopy, is the study of certain reactions that are too fast for measurement or ordinary techniques. One such reaction involves a fast exchange of protons between two molecules having protons attached to electronegative atoms with lone pairs of electrons such as oxygen. The exchange reactions between acetic acid and water affords, for example, you can see in the slide. Here I'm taking the exchange reaction between acetic acid and the water affords examples such as CH3COOH. You can see in the slide this exchange of reaction, but in a normal chemical reaction such as it will be, you can see in the figure, C8H18 in the presence of PD and catalysis, it will be converted into C8H16 and hydrogen release. So one type of hydrogen paraffinic is consumed and another type is olefinic. It's mean one type of क्या कहते हैं paraffinic and another type of olefinic is formed. So samples of reacting mixtures can be taken at frequently intervals during the reaction, and the rate of disappearance or formation of the different types of hydrogen can be measured, so that the result would be measure the rate of the chemical reaction and the kinetics involves the reactions. Thank you so much.